Okay, now in this video, we'll discuss on the basic operation of transistor. Or basic current voltage operation of the transistor. So to produce a desired mode of operation, the two PN junction must be correctly biased. So if you recall back on the topic of the PN junction, so PN junction, we have the forward and reverse bias. We have two type of bias, forward bias and reverse bias. So if you want to make sure that the diode is on, so we need to set the diode in forward bias. If you want to have the diode to block the current, so you need to set the diode to be in reverse bias. So this is what does it mean by the first statement, the desired mode of operation. Okay, NPN transistor will be used for illustration. So in this although we have two type of transistor, PNP and PN, for explanation, I will explain only on NPN transistor. But however, the explanation of PNP is quite similar to the explanation of NPN. It's the same, except the role of electron and hole in the PNP and NPN. And then the bias voltage polarity also different because of the let's say for PN junction and NP junction, although it's similar, but if fault bias, sometimes we need to apply different voltage polarity, and then the current direction is also different. So this is if you refer to the previous videos, in the symbols, you can see that the arrow of the direction of the arrow in the PN and NPN symbol is different. So actually this reflects the difference of current direction in NPN and PNP. Okay, so all are reverse. Okay, so in BJT, let's say okay, we discuss on NPN. So this is N, P at the middle, and N. So B, the middle will be the base, and then this is emitter and this is collector. So here you can see we have two junction. The first junction is the emitter base junction, and then the second junction is collector base junction. Okay, we have two junction, and for every junction we have two bias. For PN junction we have two way, either forward or reverse bias. Okay, so since we have two junction, and for each junction we have two type of biasing, so actually we have four possibility of bias condition. Okay, so this table lists all the possibility of biasing. So for example, if the emitter base is forward bias, and then collector base forward bias, okay, this type of operation is called saturation operating region. So both forward bias is called saturation operating region. Okay, if the emitter base is forward bias and collector base is reverse bias, so this is what we call it forward active operating region. And the third one, if emitter base is reverse, collector base is forward, this is called reverse active. And the last one, if both are reverse bias, so this is what we call it cut off. Okay, for your information, okay, the third one here is not that relevant, so you can ignore this one. So you can ignore the third one. So the important one is the saturation region forward active region, and cut-off region. Okay, so next slide show the application for each operating region. So BJT need to be set in certain operating point or region according to the desired application. So if you want to use the BJT as amplifier, you need to make sure that the BJT is set at forward active operating region. So this is forward active, this is amplifier. So means if you want to use the BJT as amplifier, the emitter base should be in forward bias and collector base should be in reverse bias. Okay, but if you want to use the amplifier as a switch, so you will use the cut-off and you use the saturation region. Okay, here the word cut-off here actually means the cut off the current. So there is no current. Current is 0. So this is off state. This is off state. This is off state. This is off state of the switch. And then the saturation is actually where the current start to flow and then hit the maximum current value. So this is the on state. Okay. So now you see that now you can see the importance of biasing the terminals of the BJT at certain value. So this should depend on the application of the BJT. Okay, this is the left graph is collector current. Okay, this is collector current versus VCE. VCE is the apply collector emitter voltage. Okay, so this graph is called output characteristic. So actually it's very important, it's very significant characteristic of a BJT. So in general, the BJT, the output signal of the BJT is collector current. So this is the output. So the output is collector current. So that's why this characteristic is called output characteristic. So you want to see how the output current changes with respect to the different VCE and different base current. So IB is a base current. So IB here, base current here actually is a control signal. So this is a control signal. So how you can understand this graph is, okay, let's consider this 30 microampere. This IB equal to 30 microampere. So what was done is first we flow the base current and fix at 30 microampere. So the base current is fixed at 30 microampere, and then we vary the VCE from 0. So we vary the VCE from 0 until, let's say for the example, until around 12 volt, until 12 volt, and then for each VCE, the voltage, the collector current are measured and plotted. So here we have many case of many value for value of control signal base current. Okay, so what is VCE? I forgot to explain what is VCE. VCE is a voltage at collector minus voltage at emitter. So VCE is voltage across collector at collector with respect to the emitter. So VCE equal to VC minus VE. So this is VCE. Okay. Okay. This slide I want to show you the relationship between the biasing condition and where is the saturation, where is the region, operating region in the output characteristic. Okay, for example, in this graph, this plotting already show you where are the three main region mentioned in previous slide. Okay, the first region is saturation region. Saturation region is at the very low VCE, and then it have the current start to have a significant increase. Okay, this is a saturation region, and cutoff region is where the base current is zero. The base current is zero, and then the collector current is almost zero. Okay, the collector current is almost zero. And then the third region is active region, is at the middle. Okay, at the middle of the plot graph. Okay, let's consider this biasing. So when VCE is 0.5, let's say 0.5, I think it's around here. Let's say I put here, this is 0.5 volt. Okay, around 0.5 volt. And then you consider when IB is 40 microampere. Okay, VCE is 0.5 and IB is 40 microampere. Okay, when IB is 40 microampere, so this show that there is current, there is a significant current in base and emitter. So the IB here, if the base current is not zero, so actually it means that the base emitter is on, the base emitter junction is on. So the base emitter is in forward bias. So when the base emitter in forward bias, since this is a PN junction, forward bias, the voltage should be limited at 0.7. So the voltage should be limited at the 0.7. Now we can calculate the value of VCB. Okay, so what is VCB? Okay, we use here in this circuit, you can see that the VCE is actually a VCB plus VBE. So VCE is considered as 0.5, VCB is unknown, so plus 0.7. So you got the VCB is equal to minus 0.7. So you got here VCB is defined as this is positive, this is negative, this is VCB. So if the VCB is minus 0.7, so means that the collector, so means that the 0.7 minus the minus value means that the voltage of the base is larger than voltage of the collector. And then you see this is a NPN junction. So this is base is the P type, this is N type. So P type anode has higher voltage compared to the cathode. So this is a forward bias. Okay, forward bias. So you see here, BE is forward bias, collector base is forward bias. So this is saturation region. So as mentioned in previous slide. Okay. So again, the saturation region is where the both base emitter junction and collector base junction is in forward bias. Okay. Next, we consider where the VCE is 5 volt. Okay, VCE is 5 volt. And then IB is 0. So IB is 0. So when IB is 0, so this means that This means that the base emitter junction in reverse bias, because if the voltage is forward bias, okay, the voltage is forward bias. If the voltage is forward bias, there should be a current flow. But now there is no current flow, means that this is in reverse bias. Okay, since this is reverse bias, so what happened to the base emitter junction? So you can replace it with the open circuit. So there is no connection between base and emitter. So this leaves the VCB will, all the applied VCE will be dropped at the VCB. So all the voltage will be dropped as a VCB. So VCB now this is positive, so means that VCB means positive, so means that VC is higher than VB. So VC is N-type, so this is N-type, VB is P-type, so cathode is higher than anode, so this is a reverse bias. So both are reverse bias. This is what we call it cut-off region. So as shown in this plot, this is the region of cut-off region. So this is the cut-off region. Okay, and then the last one, we like to see the biasing condition for active region. Okay, so for example, this is VCE is 5 volt, and then IB is 40 microampere. So IB is 40 microampere means that the PN junction in the base emitter is forward bias. So when it is forward bias, so base emitter junction can be replaced by the voltage supply 0.7. And then lastly, VCB can be calculated using the same equation, VCE. So VCE is equal to VCB plus VBE. Okay, VCB plus VBE. So VCE is 5 volt, VCB is the one that we want to calculate, and then this is 0.7, and then VCB you can get 4.3. So here 4.3 is positive voltage, means that VC is larger than VB. So here the collector is N-type, the base is P-type. So cathode has higher voltage compared to the anode. So this is a reverse bias. Okay, so means that in order to have the active operating region, so you need to apply forward bias at base emitter junction and reverse bias at collector base junction. Okay. In this slide, I want to emphasize on one very significant statement. Okay, the statement. BJT is a current control device. As I mentioned before, the output of the BJT usually is a collector current. So this is the output. Okay. So when we apply the BJT as amplifier, so usually we will bias, or we will set the BJT at the active region. Because of amplifier, amplifier work properly when the device is at active region. Okay, let's say here, so in this we have the voltage of, let's say this is IC naught, the IC the bias, IC naught, ICQ. Let's put ICQ. Okay. The voltage of IC, the value of the IC can be controlled by changing the base current. Okay, let's say we change to 40. So the current will increase to this point. So we have collector current around 4 milliampere. If the base current decrease to 20 microampere, okay, now we have around 2 milliampere collector current. So this is means that the collector current is controlled by the base current. So base current will be seen as the input control. This is input signal that they control. So the signal is the input signal. Sorry, the control signal is the base current. So this means that BJT is a current control device.